Hello, and welcome to the 10th in the series of Virginia Transformers customer webinars. Today's webinar is on power transformer field failure modes, investigation and prevention, presented by Hakan Sahin, who is our Director of Business Excellence.
This webinar is being recorded and it will be available on our website, and this will also go on YouTube as well, where it will be available for future viewing. If you have any issues in getting a link to the webinar recording, you can always reach out to the marketing email ID in the invite, and we will link you up accordingly.
Hello everyone. As always, we're going to start with our safety moment. Today, I would like to speak about the greatest holiday seasons coming up again. However, the fires are going to be with us. Please be careful as we decorate our houses, our work areas. Please remember the fire safety when we put out all these nice holiday decorations. Why do transformers fail? This is what we're going to talk today. However, I want to start with the bathtub curve, as it's called, the curve that you're seeing at the bottom right side of this slide. This is a statistical data from our industry that shows the failure mortality of transformers to be slightly higher at the beginning of their life cycle than the random failures during the normal operation cycle of the transformer. And of course, it goes much higher towards the end of the life cycle of a transformer. But what are the main causes? Sometimes it's almost impossible to pinpoint the exact root cause of a failure, especially if the transformer has gone through a catastrophic failure like the one you're seeing here in this picture. And it's very unfortunate that a lot of transformer failures end up turning into a catastrophic failure due to the forces and the electrical energy release during the failure. Unless we can really pinpoint it looking at the system data, once again, it may not be possible for us to pinpoint, which is why in this pie chart you're seeing, there's 27% of transformer failures in the field that really has not been determined to why they failed. Electrical disturbances, those as an example, let's talk about the faults, the short circuits. And how do we know that it failed due to a fault is A, we can look at the system data, and we can look at the mode of the failure within the active part, the core and coil of the transformer. Lightning, of course, we will talk about almost each one of these effects in the upcoming slides. But lightning, the harmonics, that we will be discussing in detail. I will connect insulation and moisture together. And as I said, we will be talking to this more in detail in the upcoming slides. I just wanted to have a good starting point and scare everyone here in the webinar about why transformers fail in the field. Before we start getting into the details of transformer field failure modes, let's start simple. Let's really touch base with the definition of a transformer, starting with the IEEE standards definition. It is a static electric device consisting of a winding or two or more coupled windings with or without a magnetic core for introducing mutual coupling between electrical circuits. So as we know, moving electrons, which is called a current, create magnetic field, and this magnetic field affecting the other electrons, stationary electrons, causing the electromagnetic force. In a very basic core form transformer that you see on the right side, I'm not going to get into details, but as I said, it's always good to start with the very basics of what we're going to talk to. So this is here as a flux being collected in the core when one winding is energized, creating electromagnetic field collected by the core and energizing the other winding by mutual coupling. And this is basically as simple as I can say how a transformer works. What are the basic, and this is very basic parts on a core form transformer? Starting from inside, of course, core, the coils, the leads, connections, cables, tap changer. Inside the tank could be mostly de-energized tap changer. There are load tap changers as well. Could be in-tank LTC, or it could be on-tank LTC. Bushings to bring the energy outside the tank, control cabinet, the cooling system, and the tank itself. And of course, the liquid could be mineral oil, FR3. These are the basic parts that makes a transformer function in the field. Let's start getting into a little bit more formulas to understand or explain the basic principles of a transformer operation. Like I said before, why not start with the basics? Because if we cannot understand the basics, then we won't be able to explain the complicated portions of the transformer failure modes. And yet, when we start talking about mechanical forces on a transformer, which is one of the #1 reasons actually why the transformers fail in the field, this is how it starts: the electromagnetic field, the electromagnetic force. So if we think about on the right side, a simple step-down transformer, the way the transformer works is, when the electrical voltage is applied to the high voltage winding, the flux that's collected by the magnetizing the core itself magnetizes the core. So the core actually turns into a big, large magnet. And the voltage is induced into the low voltage winding by the mutual coupling. And the formulas used, it's basically, because this is alternating current, it is related to the number of turns into the derivative of the flux. So the change in the flux. The change in the flux is not changing the flux density, but it is the direction. So it is 60 times a second flux rotating in the core. What are the stresses acting on transformers at all times? These three, every time I either do a webinar, training seminar, conference, or even in our plants, in our factories, when I discuss transformers with anybody, from our operators to our CEO, these three stresses here has been embedded in my blood about the transformer stresses: mechanical, thermal, dielectrics. Everything we do, when we design, when we build the transformers, when we manufacture them, these are the stresses that every component that we use must face. Mechanical stresses, due to all these electrical fields and electrical forces that we discussed. And these mechanical stresses are between the conductors, leads, and windings, due to the overcurrents or fault currents caused by short circuits or inrush currents. Thermal stresses, that is basically the main loss of the transformer when we talk about the efficiency of the transformer. The 90%, 95% of the losses in a transformer is coming from the core and the windings. And the thermal stresses are when something is overheat due to local overheating or overload currents or leakage fluxes when loading above nameplate ratings, or even malfunctional cooling equipment. I'll show you a picture later on in these slides that shows this happening in real life. Dielectric stresses could be due to system overvoltages, transient impulse conditions, or internal resonance of the windings. This slide I wanted to use as a starting point to discuss the mechanical forces. when we discuss the mechanical forces, we're going to talk about short circuits and faults. But once again, for me to explain short circuits, I like to start simple, which is impedance. We need to understand what impedance is. Coming from leakage reactance, it is the flow of load current in windings creating magnetic fields or leakage, flux fields around the windings. Flux exists in windings and in space between windings, which results in impedance between windings, or you can also consider this as leakage reactance. What is short circuit? What is fault current? As an example of a short circuit is, on a nice day, transformer is running in the field, humming and doing its business. All of a sudden, we have some storms coming, and this transformer or its power lines are running in forestry area. And all of a sudden, this transformer is fully loaded, energizing what it needs to energize, and a large tree branch falls. It can either create a short between one power line to ground, or it may create, which is the case of the worst condition, if the big, large, wet tree branch falls on top of the three-phase line. This is called the three-phase fault. What happens in the transformer when a fault occurs? So we will start with the left side, the diagram showing the magnetic fields created during short circuit event. You can see the disturbances and you can see the amount of the magnetic field disturbance. What happens to the current? So let's start going into the right side. Please look at this. The formula in the middle, it's basically, which we will explain in the next couple of slides also, the fault current is governed by the open circuit voltage, of course, the system voltage of the transformer or the system, source impedance, and the instant of fault onset. In the case of an external short circuit, the first peak of the fault current through the transformer will increase to a multiple of the rated current. And this multiple, you will see, is going to be related to the reverse ratio of the impedance of the transformer. In this slide, I wanted to share with everyone here the magnetic stray field lines of a two-winding transformers. They are always, not only just during faults, but always we have radial forces and axial forces. The stray flux has components in both directions because one actually creates the other one. For those of you who remember the college studies, it's either called the right-hand rule or the left-hand rule. Because of that, the 90-degree between the magnetic field versus the magnetic force is why we always have the radial and axial direction forces. And on the right side of the slide here is another interpretation of the same, is how we calculate the force of the magnetic fields in a transformer during operation. Now we're going to start getting into what happens when we actually create a short circuit in a transformer. What does short circuit or a fault do to a transformer? It increases the mechanical forces and even the temperature rise. Because think about it. Let's think about the simple formula. The short circuit current is a simple one version, is the rated current divided by the impedance of the transformer. So if your transformer's impedance is 10%, which means 0.1, and your rated current of the winding is, say, 1000 amps. So your short circuit current, as simple as I can make it, there's more to it, but just for this webinar purposes, it is 1000 divided by 0.1. So for that instant, for that 3, 4, 5, 6, 7 cycles until it's on set, the fault is on set. For those cycles, your current in the winding, especially for the first instant, will be 10,000 amps. So for those of us who know how to calculate power, power is related to the square of the current. So I'll just pause here and now look at mechanical stress directions. The picture you're seeing on the left side here is, imagine that gray area is the core. The first red area is basically a cutaway drawing in a way, in a simple version, is the inner winding. Let's think about this in this case as your low voltage winding. And the second one, further away from the gray shaded area from the core, is your, let's consider as the high voltage winding. So the mechanical forces, when faults occur, will try to squeeze the inner winding. I call it squeeze. We'll use the better words in the next slides. But it will try to squeeze the inner winding towards the core steel. And for the outer winding, for this case, for example, it is the HV, it will actually try to expand the high voltage winding, push it outwards. So inner winding will try to reduce its radius, and the outer winding will try to increase its radius. And then what happens to the winding height? Let's see that on the next slides. Here on this slide, I want to show as a different interpretation of what the radial forces do to windings. So as I said in the previous slide, for the inner winding, the radial forces creates compressive stresses inwards, and the outer winding, it creates the tensile stress. Now, these are the words that if you sit through a design review or you speak with an experienced design transformer design engineer, these are the stresses, radial stresses, that you will hear them talking about. So now we are starting to understand where they are coming from. Now remember though, the topic of this webinar is field failures. And now we are talking about one of the most common causes of transformers failing in the field. And we will discuss, once we understand the mode of this failure, we will speak about what we can do to prevent them from happening. Continuing on the radial forces result in the buckling for inner windings, increasing the radius of the outer windings, and here is a new one for you guys, is spiraling of the end turns of the helical windings. The radial component of the leakage flux creates forces in axial direction. Remember 2-3 slides ago, I was talking about the right-hand rule or the left-hand rule. This is, once again, it's coming in effect here. It's the magnetic field and the magnetic force. Please pay attention in the middle. When the magnetic field reduces, the magnetic force increases. The other thing that, which is actually the axial short circuit forces accumulate towards the winding mid-height. That's the demonstration in the picture. And once again, the left side here is the gray shaded area is the core and your inner winding and the outer winding. However, I want to specifically point out here, in that left side of this, where we have the two windings and the core, please pay attention to the winding mechanical height. What's winding mechanical height? What's winding electrical height? The mechanical height is the complete height of the winding with the conductor and the blocks that's holding the winding in place under pressure between the two pressure support plates. So here, specifically, it's drawn showing the mechanical heights are perfectly equal. So what happens if we start to create axial imbalance, which will create extra axial forces? Now, once you start, once again on the left side, once the windings start having mechanical height imbalance, then look what happens in the middle, the magnetic field, and of course, the result of that is the change, really much, a lot of change in the magnetic force. This is the demonstration in this slide that we want to share with you. Now, you may say, Is it just when the fault? Well, of course, when the fault occurs, the transformers, remember 3-4 slides ago, the transformers not only will see radial forces, but axial forces. Radial forces, as we said before, will try to compress the inner and push the outer winding out. But it will also try to push the inner winding downwards and the outer winding upwards. Let's see that on the next coming slide. Let us look at some examples showing buckling of the windings. These are some ugly examples from the industry. I don't know who the supplier is. It's not the point of the discussion here. But the point of the discussion here is for us to share this experience with you all in this webinar. So if you look at the left picture and the middle picture, it is a very typical, and of course the right one too, but it's the view is different. This is the very typical buckling of the inner winding, where the inner winding, the compressive forces, where the inner winding could not withstand against the compressive forces, which were trying to squeeze this inner winding towards the core steel, like I said before. If you look at the right picture, the picture on the right side of the slide, it's very evident how the inner winding has buckled. So now the question you probably have is why? And the answer we will discuss more on the upcoming slides, but I like to talk to the picture. Why? The why could be the design engineer might not have called for the correct hardening of the conductor. When we calculate short circuit forces, we calculate them using the impedances, the system impedance, and everything else of the rate current of the winding and the short circuit current, of course. Then our softwares, our calculation programs tells us what the minimum hardening needs to be, in addition to many other factors, of course, but I'm simplifying it here. And we have to order that conductor with that hardness level. What if the design engineer of this transformer here that you're looking at did not pay attention to that? Or what if that the supplier of this transformer ordered the correct required conductor, but their supplier, the conductor manufacturer in this case, did not send them the required hardening? What if the manufacturing made a mistake? What could they have done wrong? The inner windings, we designed them to be self-supportive as long as they are manufactured tight around the core steel. What if the manufacturer of this winding did not produce a good tight winding? So please pay attention here what I connected here, and I'm going to connect it with what I said earlier. There is design, there is materials, and there's manufacturing practices that can all fail a transformer. Axial force failure mode. What are the axial force failure modes? Collapsing of the winding end supports. So look at the middle picture, and right above the conductors, you see what we call pressure rings, or some companies may call it winding tables. It's basically that big, thick, special material ring that is used to keep the coils under pressure using the jacking mechanism that the manufacturer has. So that big, thick ring actually is used to distribute the mechanical force that we keep these coils under pressure. The force is calculated mainly using the short circuit, the fault forces of the transformer. Even the thickness of that material, how many key spacers per column that we're going to use, everything is defined using those short circuit forces and clamping forces and even the lifting forces. There's so many different aspects of calculating of this tie plate and applying the jacking pressure on the windings. So This ring has been broken, obviously, you can see in this failure. So this is actually a short circuit failure mode that has seen in the field. So the axial forces, which are actually the result of the radial magnetic fields, can cause collapse of winding and support, like I just discussed, tilting of winding conductor, and tilting I am showing you here as a picture demonstration in the middle down picture. So is the tilting now, some of you are asking this question, is it because the conductor hardening is not okay? No, maybe, but really the tilting may occur in this case really if the winding has not been wound tightly. Telescoping of the windings, I spoke about that earlier, that the axial forces will try to push the outer winding upwards, which is what actually created in this picture the collapsing of the winding and support here, the pressure ring. Bending of the cables between spacers, that's the picture on the right side, and I actually have a real life picture coming up in the next slide. And of course, damaging of the conductor insulation. Here are some more examples of axial forces causing mechanical withstand of insulation material and the risk for tilting. If you look at the picture on the right side, that is not how a conductor is supposed to look like, and that's not how it looked like when it left the factory, I'm sure. But this case, now there's a difference between tilting versus bending. Why? Remember the Y factor? I said earlier, the tilting could be due to a manufacturing defect. The bending could be due to, once again, the hardness of the conductor. Could be design or could be the supplier. Let's start summarizing short circuit risks on this slide. However, before I start summarizing, I want to emphasize that short circuit forces are not the only mechanical forces that the transformers see. There's, of course, the transportation forces during shipping and handling of the transformers. So we, as manufacturers, we must design and build the transformers to withstand the mechanical forces that they will see during transportation. How we anchor the core and coil to the tank, the cover, the bottom, the sides, and all of the above is very important. Because if the core and coil is not anchored correctly within the tank itself, and by the time it gets to you all, to our customers, then the active part, the windings, the leads might have already shifted. Remember, the mechanical forces due to short circuits is not just within the windings. That is the worst case scenario, of course, but the leads. So we as suppliers have to make sure that all these leads, the LTC leads, the high voltage, low voltage connection leads, are ran through very strong structures and secured very strongly, because those leads, they are in the magnetic field after all. They're going to see short circuit forces. So let's look at some of the risks. Through faults are often the cause of transformer failures. I think I said that enough already. Many older designs have insufficient margin for today's fault currents. Now, some of you may say, no, older transformers are better. Well, I agree and disagree. The agreement is, yes, I have seen 80, 90, 100-year-old transformers still running in the field. But I also know the help of the computers and the softwares allowed us to see the magnetic fields and have better calculations that we did not have back in those days. Loose coils. What loses the coil? I will leave it as is now, and we will talk about that in the upcoming slides. Normal aging can cause brittle insulation and increase failures. Even brief overloading may cause significant aging. And once again, we'll talk about that coming up. Oxygen in the oil can double the aging rate. Please, 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 I'm going to underline that. Oxygen in the oil can double the aging rate. We will talk about this again when we come to the slide about the cellulosic material. Moisture. Again, I have a slide that will actually demonstrate with data for you all what oxygen and moisture together with the temperature does to insulation. Temperature rise in windings during a fault. After talking about the principles of mechanical stresses on transformers that can happen in the field due to short circuit faults or even transportation, now it's time for us to get into the thermal stresses. Thermal stresses is one of the main killers of the transformer, which is because of the cellulosic materials aging. In this slide right here, I'm not going to read every one of them one by one, but it is really to give the idea of how temperatures relate in respect to the winding height. As we know, the source of the heat in transformers, the two main sources are A, the conductor losses due to I square R current flowing in the windings, and of course the core losses due to magnetic flux in the core material. So if we consider the ambient temperature steady, you can see here in this slide how the different temperatures are related with respect to the winding height. In a traditional cooling system, which is natural oil flow in transformers through the radiators, as we know, the heat rises and goes through the radiators and cools down, and from the inlet comes back into the transformer. Here you can see that the tank oil versus winding oil. Now, someone may ask the question, what's tank oil and winding oil? It's basically, tank oil is the all over the oil inside the tank. Winding oil is the oil which is closer in prosperity to the windings. Then you can see the winding copper is the house in respect to everything else. And of course, winding hotspot, which is what we are going to talk in detail in the next coming slides. I think in this slide, I don't really have to speak much. The picture speaks 1,000 words, obviously, but these are some of the field failure pictures of extreme aging from thermal. This could be due to continuous overloading, not enough cooling of the transformers, and this can actually be due to fault currents not being stopped on the right timing of the failure. Because remember, the fault current multiplies by the reverse ratio of the impedance. One thing I do want to emphasize in the picture on the left, though, is you can see the second and third conductors, the discs, actually have arced. That is a dielectric failure. So what I'm pointing out here is, as our insulation degrades, ages, and starts to fail, that is going to cause the insulation integrity failure reduction of our transformers. And of course, as our insulation integrity reduces, then the strength against dielectric forces, which we will discuss, reduces. So even a simple transient voltage or a lightning event will cause this transformer to have a dielectric failure, but the true cause behind everything could be that the insulation have aged due to thermal stresses over the years and just could not handle the dielectric strength anymore. This is one of my favorite slides that I like to talk to. We're going to talk about cells. For those of you who has seen what is in the tank of a power transformer, of course we know the oil, the conductor, the core steel, the clamps, and everything else. But the main insulation that we use is paper, cellulosic material. Of course, there are special papers, there are special woods, but still, at the end, they are
cellulosic material. Of course, we use other insulation materials too, like Nomex, fiberglass, and such. But the main insulation, once again, is cellulosic material. So we need to understand the chemistry of the cellulosic material to be able to explain why temperature affects so much. And we're going to talk about the degree of polymerization. Let's start with looking at this cellulosic fiber chain in the middle of this slide. I'm not a chemist engineer, so I'm not going to sit here and talk about all the C's and H's and all that. But I think every one of us here in this webinar knows what H2O stands for, which is the main atomic structure connecting all the C's and H's and O's in this fiber chain. H2O is water. So water is the main connector of all the chain in the cellulose fiber. And as we all know, water vaporizes at the temperature of 100 degrees C. Now let's sit back and think. What is our transformer's winding temperature rise per our standards? 65-degree winding rise. So if we assume the 30-degree average ambient, 30 plus the rise is 95. That is the reason why in our IEEE standards committees we define 95 as the average winding rise. Because what happens when the average winding rise goes beyond 65 degrees, or the ambient where this transformer is operating goes beyond 30, 40 degrees, which as we know, summertime in hot states, the ambient will be over 30 degrees. Summertime, hot states, we're going to overload these transformers. So what do you expect the temperature to be in the windings? Way above 100 degrees. So what happens when the temperature is way above, around, especially the conductor, and the blocks that is holding these conductors, the windings together, then the cellulosic fiber chain is going to start breaking because of the main connector, which is H2O, vaporizing. Degree of polymerization is a measure of the number of intact chains in a cellulose fiber, and it provides an indication of the ability of the transformer insulation to withstand mechanical forces due to through faults and etc. So that's what I was saying earlier. Imagine that we overload our transformer, overload for 3 months, hot conditions, and run them really hot. Then a lot of moisture is going to break away from the cellulosic fiber chain. When something leaves, this is a typical atomic structure for anything, including ourselves as human bodies. As we age, we shrink. As the cellulosic material or the insulation ages in transformers, they shrink and causes the windings not to hold the jacking pressure anymore. They need to be held against the short circuit forces. What affects the degree of polymerization? Let's look at the degree of polymerization of the insulation affected by these conditions. Moisture, definitely. Acidity of the oil, oxygen content, and of course, temperature. Remember earlier in one slide when we were going over just generic causes of transformer failures, that was moisture, that was oxygen, and that was temperature. And I said, I will leave this alone for later to talk to. And this is where we are going to start getting into that. The degree of polymerization is measured by the viscosity measurements according to the ASTM method after dissolving the paper samples in a cupriethylene diamine solvent. Paper samples must be taken from enough different areas in a transformer in order to get a profile. When combined with the detailed design knowledge, the measurements in one area of the transformers can give information on the condition. Now, what does this mean? And how are you? You're not going to go inside the transformer and take a paper sample. Please don't do that. What you can ask our suppliers to do is put extra key spacers or insulation material between your windings for you to remove it 10 years, 12 years, 5 years, depending on the cycle that you're running, the loading cycle that you're running your transformer at, and carefully package them and send it out for DP tests. And this can actually help you identify how much the transformer have aged already. On a brand new transformer insulation, the DP is approximated to be around 1,000. Now, keep this number 1,000. What is this? 1,000 years life expectancy. So when we ship these transformers to you, the insulation that we give to you is minimum 1,000 years, as long as they are kept and ran with the conditions that we're going to talk about. However, for those of you who may know, what is the average age of transformers defined by the standards to run in the field at full loading and everything else? Believe it or not, it's 22. What is the average age of the transformers in our country right now? It is close to 50. So what happened to 1,000? Well, because we don't run the transformers at just no load. We run them at full load. We run them at temperatures. We don't have perfect water content. We don't have the perfect moisture level, acidity, dryness, cleanness, and so on and so forth. So let's look at this chart here. And let me walk you through the 100 degrees, okay, the x-axis. So find the 100 degrees and go upwards. The blue line is if the water, at the same reference 100 degrees that the transformer is running, if the water content is around 3 or 4%, the expected life of the transformer will be less than 10 years. With the same 100 degrees, if we go to 1% water content, then the life expectancy immediately jumps close to 20 years. Now, with everything dry, clean, acid level low, if everything is good in the transformer, if you run this transformer at 100 degrees temperature constantly, then the life expectancy will be over 20, 22 years. The change is a lot. Of course, we run our transformers at 110 degrees, we run our transformers at 90 degrees. So if you study this graph more in detail, you can understand, as I did years ago, the importance of not only the temperature, but the effects of other factors aging our transformers' insulation. And if the insulation ages, transformers' life expectancy reduces against mechanical stresses and dielectric stresses, as we saw in the picture before. All right, we completed talking about mechanical stresses. We completed talking about thermal stresses. Now it's time for us to talk about the third killer of transformers, dielectric stresses. So let's understand dielectric stresses. Overvoltage integrity. Overvoltages can be divided into two classes: continuous overvoltages or transitory overvoltages. Continuous overvoltage is related to the core and its magnetization. Okay, for those of you who attended my last webinar on reverse power flow, we actually talked a lot about overvoltage. We talked a lot about transformers having been designed to run at 105% no load voltage with 0.8 power factor and full load, or 110% continuous overvoltage with no load. Transitory overvoltage refers to intermittent stresses placed on the insulation system, usually as much higher levels than the power frequency stresses. So these are under the overvoltage categories. Then the transient voltage category, lightning and switching impulse surges are called the transients because their duration is short. We're talking about microseconds. For those of you who has witnessed tests or tested transformers, as you know, we discharge lightning in 1.2 microseconds, and the zero crossing is generally around 100 microseconds, with the tail time being around 50 microseconds. So that's why it's called the transient stresses. The frequencies are much higher than the power frequency. The transient calculations are used to find the time-dependent distribution of transient voltages. applied on the line terminals over the winding. So we'll see that what this means in the next slide. So dielectric design against these transient voltages or overvoltage stresses, in order for us to design, we have to understand the impulse voltage distribution, for example, in this winding. The schematic here shows the capacitances, resistances, and inductances of a transformer. The initial distribution may be approximated from the capacitive response before inductive components take effect and neglecting resistive damping. Okay, remember, transformers are RLC circuit. There's resistance, there's capacitance, and there's inductance. Initial model is network of series capacitances between the disks and shunt capacitances between windings and the ground. So knowing that the impulse stress needs to be migrated initially because it's so quick. So it's the first 3-4 microseconds is the most important. And the capacitor has to take that first, as I always say, the first punch. We look at how we can increase the capacitance value at the start of the windings to withstand these dielectric stresses. So I put some illustrations here for you. Once again here, this presentation is available and it will be available on our YouTube channel also, or you can send an email to the email address that you will get at the end of this presentation. Of course, we will share that with you because this is the purpose of the webinars, is sharing knowledge with everyone. The more we know, the better we get. So other than getting too much into details here, what I wanted to emphasize here is the dielectric stress distribution in the winding is first taken by the capacitance of the winding and distributed throughout the windings of through the inductance of the winding. Of course, there's resistance, but it's constant. So how does the dielectric impulse stress distribute through the winding? I wish it could be linear. It's not. It changes from winding to winding. It changes from the geometry of the winding. So it's our responsibility as the design engineers, using the most sophisticated softwares that we have, to be able to plot these dielectric stresses. So going from left to right, in the left, you can see if a lightning hits the top of the winding and the bottom is grounded, and that's actually how we do the lightning impulse test, the voltage distribution varies depending on the winding. So we have to estimate the linear function from so many different variances of this distribution and try to plot these. And now comes to definition of how much paper we're going to use around the conductor, what distance we have to leave or give between the disks. So if you look at the picture on the right, that is a field failure, dielectric field failure. It may cause or may not cause a catastrophic failure in the field, depending on the protection system. But what you can see here is the very bottom, right under the first disc at the bottom, there is a ring there that has paper covering on it. That is a static ring. That is your capacitor that's actually connected to the very first turn of that winding. Then we go to the first disc and the second disc. So in this picture, you are seeing a dielectric arc between the two discs. So now you can ask this question during the investigation: why did it arc? Very good question. Why did it arc? Did we not design it right? Then you look at the other two phases. Did we damage the insulation during manufacturing? I don't know. Did we have contamination in the oil? Anything is possible. Or did the insulation age? So this is where the investigation steps comes in, where we have to have a lot of data. The really good investigations actually rely on data to be able to collect it all the way from the factory manufacturing, factory design, factory shipping conditions, and also one of the most important is field maintenance. Transformer field failures, some of the data here is top transformer failures. This data is gone from Doble. 43% failure causes relate to winding insulation. Almost 20% bushings and 16% tap changers. So this is a critical number here, 43% winding insulation. If anyone asks, is it due to mechanical, thermal, dielectric, well, it could be all of the above or one. This is why we are doing this webinar, to connect those three stress points together and allow our end users to have a great understanding of what makes a transformer fail or run perfectly fine in the field for years to come. Other areas of concern is pollution, dust, debris affecting the bushings and cooling. So where you install this transformer will affect the life of the transformer as well. Cooling system inefficiency, cups tank elevation, that's the conservator tank. Some specific issues could be streaming electrification, nitrogen gas bubble evaluation, blocking some of the clamping. These are some old styles, but it has had common factors. Shell form rewedging, or some of the old GE type U bushings have known to cause some failures in the field. I will share some field case studies here from some of the field failures that I have known or gotten involved or heard from my colleagues from this industry. This is a Deenergized tap changer. As you know, Deenergized tap changers generally are on the high voltage windings, and they are, the name for Deenergized is because they are supposed to be operated only when the transformer is de-energized. However, the failure that you're seeing, the arcing between the two studs there, is not because anybody tried to turn it when it was energized. It was really only, before that though, let me explain the Deenergized tap changer, how it's really designed. Very simply here, if you think about a high voltage, simple high voltage winding, you have a start lead, then you put the main body turns and you come to the tap section area, then you start pulling 1, 2, 3 leads out. Between each lead, you have 2.5% ratio. And then there's a break between the top and the bottom halves. Then 3 more leads, 2.5% ratio in between. And then you finish the rest of the winding with the second half of the winding. So the connection of the top half and the bottom half of the two windings happen via the tap changer. So what you're seeing here is the nut that's connecting the bolt on the stud has gone loose over time, and this tap changer lead has shifted and one lug had touched the other lug. So you basically created a short within the winding via over the tap changer itself, and that of course will cause a failure. Here's another example of a field issue. Looks like the issue probably got reported as a high gassing, hot metal gases. Then through the investigation, the picture on the left is the core clamp. The core clamps are used to keep the core and coils under pressure, and they are also used to anchor the core and coil to the tank. So the picture on the right is a picture where this core clamp was connected to the tank, anchored, to hold the complete core and coil to the tank. However, you're seeing here that the core clamp and the connection point were both painted, and the grounding of the core clamp was expected via this area. So at this point, the clamp, of course, gets energized too. We have magnetic fields everywhere inside this tank. So what happens is clamp grounding point had high resistivity, caused hot temperature of the metal, which actually gassed the mineral oil in this case. Here's an example of a bushing connection. This is an external issue, but please understand, what is externally connected is internally connected too. After all, this bushing has a draw lead inside, and the other end of the draw lead is connected to the winding. So if you have such a high resistive point due to a bad connection outside, that lead is gonna, not only that connection point, but the complete high voltage lead is gonna get hot. So it may actually come out as a hot gases, and it could be cellulosic gases like methane and ethylene, that you may think that the transformer inside is having a problem, but the whole problem was actually related to a connection externally. Okay, on this slide, I'm not going to say anything. The picture is very clear. The radiator bank was shut off. So the oil was not going through the radiators to cool the transformer. So the transformer was running pretty hot in this case. I put this slide here for your reference. I'm not going to read each one of them, and I think we are going to run out of time anyway, but please get in touch with us if you have any further questions or comments. But these are some of the field monitoring and diagnostics techniques that you may follow. I'm sure you do follow, but if nothing else, in any of these DGA, I love DGA, and there's one more technique or the test that I actually like for field monitoring that I will speak about in the next slide. Dielectric frequency response test, DFR. This is not SFRA, this is DFR. The DFR test is a series of power factor measurements at multiple frequencies. It's a special test equipment, and this is what it does. It provides more information about the dielectric behavior of the insulation system. The method to be used to diagnose the following conditions in transformers: moisture in the cellulose, high oil conductivity due to aging or overheating of the oil, chemical contamination of cellulose insulation, carbon tracking in cellulose, high resistance in the magnetic core steel. This is a very good test. And if you have transformers, you don't even have to have any concerns, but after 5 years, 10 years, if you want the DFR to be done with some experts, they should be able to tell you the life expectancy of the transformer if it is done by real experts.
In closing, thank you so much for attending to our webinar today. As we said at the beginning of our slides, if you have any further questions, if you would like to discuss this topic or any other transformer related topic with us offsite, please email to sales@vatransformer.com email, as you can see in this slide.
That's all from me. Thank you very, very much for attending and attention. So now we will take some questions. Thank you.
Well, it looks like we don't have any questions today.
Okay, maybe give it another minute. Okay, so there's a question.
Yes.
Yeah.
What about on line PD? How frequently is it required?
I'll take that. This is Hakan. The online PD depends on the usage of the transformer, of course. If it were my transformer, I will try to do that maybe every 3 years. That will be a good frequency to do it. And of course, another answer is after an event, that will be recommended as well.
Okay. Looks like that's all we have. Are there any other questions?
Okay.
Okay, thanks. Oh, there's one more. Okay.
What is the relation between online PD and DGA?
What's the last word? Deep day? I couldn't hear that.
DGA.
Oh, DGA. DGA stands for dissolved gas analysis, and it's basically an oil gas testing done by after sampling of the oil. However, there's also online DGA test equipment as well, which is connected to the transformer and goes, it has inlet and outlet that continuously monitors the oil gases as the transformer is energized in the field. PD stands for partial discharge, so it's an electrical activity. Dissolved gas analysis is basically the result of electrical activity or heating or anything that shows up in your oil samples.
This is Parminder Hakan. I may add to that. So DGA would show you various activities, heating and also partial discharge. When you measure PD, just measuring the partial discharge will not show other things. And DGA alone will tell you what is going on, but PD could be one of the diagnostic tests which you could do if that is the case. If the DGA is showing PD activity, then it is recommended to test that. But DGA is very commonly used in the industry as a routine, any transformer from small rating to the biggest rating. And PD is not very common. And I think most applicability of that is 230 to 345 kV and above.
Yeah, and the other thing I would like to add, the PD monitoring in the field, they are very effective for external PD measurements. But if you were having a partial discharge within the windings, they may just tell you that you have a PD, but you may not know where the PD source is, which is why, as Parminder mentioned, is you do your dissolved gas analysis and look at each gas has a different meaning to it. So if you see a lot of hydrogen, then you may think about there's a PD. If you see ethane, ethylene, methane, so there's actually very good literature on understanding the DGA results available online.
And that's all we have.
All right, very good. Thank you very much.
Okay, thanks, everyone. Appreciate your participation again. And these webinars do carry continuing education credits. So if you would like to get a CEU certificate, please email marketing@vatransformer.com, and we will send that certificate out to you. Thank you.
Thank you. Bye.
Thank you.